Principal component analysis (PCA) and factor analysis (FA) are both statistical methods that can be used to analyze questionnaire data based on Likert scale. Principal components analysis, abbreviated PCA, for analyzing data extracted from a questionnaire or a survey. In this presentation, description of the PCA will be provided, and the common uses of the PCA will be mentioned, and the assumptions that have to be fulfilled before performing the PCA will be listed, and a short description how to input the data into one of the statistical software, and finally how to interpret an output from a PCA. Principal component analysis is a multivariate statistical techniques or a method that deals with data that consist of multiple variables or multiple items. It is an unsupervised statistical method. The objective of performing PCA is to reduce the number of variables in a data set. So it is dimensionality reduction method. It aims to reduce larger number of variables that is extracted from a questionnaire or a survey. Variables are items or questions. The objective is to reduce this large number of variables into a smaller number of variables that are, or a smaller number of variables grouped together, and these groups are called principal components. So the objective from performing the PCA is to reduce the number of variables and arrange these variables into groups called principal components. These components explain most of the variance in the original variables or data. Items within these components or variables or questions are correlated. The overall objective from performing PCA is to have a large number of items or variables. Try to reduce that number by grouping those items or variables into components. These components or variables within these components are correlated to each other. So what are the common uses of PCA? When a researcher starts to design a new questionnaire or an instrument or a scale, then a PCA is a useful statistical method. The objective of performing that method is to check if all or some of the items load into construct. If some of the variables are not sufficiently representative of the construct or the section within the survey or the instrument or the questionnaire, then remove those variables from the measurement scale. So PCA can be used to when designing a new questionnaire to check which items loads into certain sections or construct within a questionnaire, and those that they do not load to this construct or they do not correlate with the variable within that construct, then remove that item or variable. The second use of PCA is to reduce the number of variables in a construct. So it is called construct PCA. If a construct consists of, let's say, up to 12 variables, then PCA can be performed to find out what variables within that construct, which is part of the questionnaire, that are highly correlated and represent the construct. The third use of the PCA is to shorten questions to be included in the questionnaire. Shorten these items or questions or variables into fewer items. So another objective is reduction. So if more than one item measuring same construct, then remove that item. And that will help to design a scale or an instrument that can be accomplished and completed by participants. So what are the assumptions that have to be fulfilled before performing PCA? The first assumption is that multiple variables are measured at a continuous level or ordinal. So the data or the responses collected from participant completing the questionnaire, it can be an ordinal based on 5 Likert scale from 1 to 5, or 7 or 9, and so on, or the responses can be a continuous variable. So there should be a linear relationship between all variables if they are continuous. PCA is based on Pearson correlation coefficient. The method also can be used for ordinal data such as Likert scale. Linearity can be tested using a matrix scatter plot. The second assumption is sampling adequacy. There have to be enough number of participants. There have to be 5 to 10 participants per question or per items as a minimum sample size. Using rule of thumb, 10 participants per question can be considered. And the way to check, or the method to check whether there is a sampling adequacy, is to perform a Kaiser-Meyer-Olkin sampling adequacy that will measure the sampling adequacy for all overall data sets. The third assumption is that the data should be suitable for data reduction, sufficient correlation between variables to reduce variable to a smaller set of components. Though there should be a correlation between items, that correlation has to be within a certain values from 0.3 to 0.8. The Parlet test of sphericity can be performed to test this assumption. The fourth assumption is that there is no significant outliers, and the fifth assumption is independent variables are correlated to each other. Another assumption is that principal components are assumed to be independent of each other. And finally, there should be a homoscedasticity in which the variance of the data is constant across all levels of the independent variables. In this slide, a print screen from a SPSS software has been inserted here. When performing PCA in SPSS, the following boxes need to be ticked. First of all, the correlation matrix, tick for the coefficient for correlation and the significance level for correlation, the determinant, which is an important values for testing the data and whether it is enough to be used for performing PCA, and also tick for the KMO and a partlet test of sphericity for sampling adequacy. The next slide gives options for selecting the method for analysis, which is the principal component analysis, and the eigenvalue is selected to be greater than 1. For performing the PCA, the method for rotation has to be decided in advance. There are two types of rotation. That depend on the variable, whether they are correlated. If the variables are correlated, then the direct oplimen will be used or the pro max. When the variable are not correlated, then the method to use for rotation is orthogonal, and there are several methods: varimax, equimax, and quantimax. The output that will be generated from the PCA analysis, there should be important things to look for. There is no missing scores. To check for the correlation coefficient, which is the R, the Pearson correlation coefficient, the value for determinants, and the KMO and partlet test for sample adequacy and sphericity, the setting for the eigenvalues, the total variance, the scree plot, the values for communalities, and the rotated matrix, with finally the table for the component transformation matrix. So this is a table extracted from a PCA analysis in which a correlation matrix has been generated for 9 items, item number 1 to 9, and the correlation between pairs of these pairwise of these items is given here, with statistically significant values shown here. And as shown here, that there is a perfect correlation between item 1 and item 1. And with item 1 and 2, the value is 0.65, and with item 5 and 1, it is 0.02. For the correlation values need to be, which is the R, need to be less than 0.8 and greater than minus 0.8. And the determinant has to be greater than 0.40 and 1. The next slide shows an output for the KMO and Bartlett test. The value need to be for sampling adequacy to be greater than 0.5, and ideally anything greater than 0.5 will be acceptable, but the higher the better. The p-value should be less than 0.05, and for the eigens values when performing the PCA, the eigenvalues set out as greater than 1. So what does this eigenvalues mean? It represents the variance explained by each principal component. Higher the eigenvalues, the more variance is explained by the principal component. Here is a table extracted from a PCA analysis, as shown here, the total variance explained. There are here 8 items, and as shown in the section here, extraction method, principal component analysis, there are 8 items, and those items have been grouped into 3 major components: component 1, 2, and 3. Component 1 explains 27.3% of variance. The second component explains 25.7%. The third is 19.1%. The 3 component explains 72.2% of the variance. The next slide shows the scree plot. Scree plot assists in determining the appropriate number of principal components to retain or to obtain from the analysis. It is used to visualize the eigenvalues and identify the point at which the curve levels off, suggesting that the optimal number of components to retain. Here in this graph, it shows that on the x-axis is the component number, on the y-axis is the eigenvalue. There, the cut point for the eigenvalue is 1, and there are 3 major components, 1, 2, and 3. The next slide describes a terminology called communalities, which is a table generated from the PCA analysis. Communality is the proportion of variance in each variable that is retained in the principal component. So the value for the communality ranges from 0 to 1, as shown here in the table. The first item has a communality value of 0.8, the second 0.7, and so on. The next slide describes factor loading. Factor loading is a measure indicates the strength and the direction of the relationship between variables and principal component. The higher the factor loading, the stronger the relationship. Factor loading is a coefficient, and the cut for factor loading as a rule of thumb is 0.3. Some people use 0.4, and some people become more stringent and use 0.45. So aim for a high value, which is 0.9. As shown here in the table extracted from a principal component analysis using a varimax method for rotation, these 9 items has been grouped into 3 components, component 1, 2, and 3, as shown in this rotated component matrix. The first component have 3 items. These 3 items, item 4, 6, and 5, loads together on that component, and the loading factor score is 0.88, 0.7, and 0.7. So those 3 variables loads into that component. For the second component, there are 3 items. Item 1, 2, and 3 loads into the component 2, and the value for the factor loading is 0.9, 0.8, and 0.79. And finally, the third component have 3 items loaded into it. Item 7, 8, and 9. With the first one is 0.89, 0.7, and 0.65. All these 3 items load into the component principal component 3. So the overall analysis from the PCA has managed to group these 9 items into 3 components. Another output that can be generated post PCA is the component transformation matrix. The component transformation matrix will look at the correlation between component number 1 correlation with 1, and 1 with 2, and 1 with 3. So if the components correlate to each other, then this will help in determining the rotation method. Then use oblique rotation, whether it's direct, oplement, or pro-max. When the components are not correlated, then use orthogonal rotation, such as varimax, equimax, and so on. And how do we determine the cutoff point for correlation or no correlation. A value of correlation between two components of greater than 0.32 indicates correlation between the components. Factor analysis is a statistical method that is used to analyze data extracted from questionnaire or survey. In this presentation, the factor analysis will be defined and described. Then the types of factor analysis will be mentioned, and then the assumptions required to be fulfilled before performing factor analysis will be listed, and finally there will be a section for interpreting an output for factor analysis. So what is factor analysis? Factor analysis is a data reduction statistical techniques. It is aimed mainly for data extracted from a survey or a questionnaire in which there are multiple items or questions, several questions, and the objective of performing factor analysis is to group these items or questions into groups or factors. So it is a statistical method that is designed to identify dimensions and factors, constructs, or sections in variables. Variables are the items or the questions. So the objective is to identify factors or constructs or groups and items that measures or measure that factor or constructs and load on that factors. So the factor analysis will examine and assess the correlation between those multiple variables, then identify groups of variables that are highly related so they can be assigned to a certain or specific factor or construct or a group. Then the questions will be grouped. Furthermore, the factor analysis will explain common underlying factor or factors or constructs. So the objective of factor analysis is to examine and assess and find if there is a relationship between items, then group them into factors or constructs, and then discover if there is an underlying structure, factor structure that represent or measured by those items. The factor analysis will uncover and generate a set of latent factors, and also it will assist in developing a theoretical model, identify any trends in data, and then determine the number of factors in a data, whether it is called factors or constructs or sections or dimension. It's all a group of items that hold together and measure factors. What are the types of factor analysis that can be used for in analyzing questionnaire or survey data? There are several types. The first one is the principal component analysis, which is abbreviated PCA. It is a reduction method, aims to reduce the number of items from a survey or a questionnaire or a scale or an instrument. It is designed that it will try to find a correlation between those items or questions and then group them into a component, and that's why it is called principal component analysis. The second type of factor analysis is exploratory factor analysis, abbreviated as EFA. The EFA can be called also principal factor analysis or principal axis factoring. The aim of performing that factor analysis is to explore the data, the items or the questions, and try to find if there is an underlying structure for these items by finding if there is a correlation, and then group them into factors. So the objective of the EFA is exploratory, to identify common factors and unique factors. So it will aim to explore where there is a factors and the structure of the factors, the number of items or questions that can measure or represent that factor. The third type of factor analysis is a confirmatory factor analysis. Confirmatory factor analysis is performed post exploratory factor analysis. So the objective of factor analysis is to examine and identify if there is an underlying structures for the items, and then put and assort or assign the items to factors. The role of confirmatory factor analysis is to confirm or disconfirm the factor structure. So the CFA is the initial step for structural equation modeling. So what are the assumptions that have to be fulfilled before performing the factor analysis? The first assumption is the adequacy of sample size. The number of participants that filled or answered or gave responses for the items in a questionnaire have to be sufficient. Rule of thumb is that for each item there should be 10 participants or more. The second assumption is that there should be no outliers, no extreme values. The third assumption is that there should be a linear relationship among variables. The fourth assumption is multivariate normality, that the variables follow multivariate normal distribution. The fifth assumption that have to be fulfilled is there is no perfect multi-collinearity, which means that items associated or linked to each other with a high value. So there should be no high correlation between two or more independent variables. So the correlation between variables have to be not high, otherwise this could indicate multi-collinearity. The sixth assumption is that the data has to be interval or ratio continuous data. However, the factor analysis can be applied for ordinal data. Ordinal data such as Likert scale, 5-point, 10-point Likert scale. The seventh assumption is the common variance, which states that the observed variables share common variance explained by the underlying factors. The eighth assumption is independence of factors. Factors are uncorrelated with each other. And the ninth assumption is that no rotation of the axis. Factors are unrotated at the initial analysis. The next slide is an screenshot taken from an SPSS software when performing factor analysis. As shown here, there are several methods that can be used for extraction in factor analysis: principal component analysis, principal axis factorings, image factorings, and other methods. On the right hand section, it shows that the method for extracting in factor analysis is the principal component. When the factor analysis is performed in SPSS, an output is generated and a table is generated for the correlation matrix. Correlation matrix shows the relationship between all pairs of variables. Here there are 8 questions, and this matrix shows the correlation between all the possible pairs of those items or questions. As shown here, item 1 with item 1, there is a perfect correlation. Item 1 with 2.6, the correlation value, which is the R value, is 0.66, and for 1 and 3 is 0.62, and 1 and 4 is 0.042. So there is a correlation between item 1 and 2. Between item 1 and 4 there is a weak correlation, and also a significant, statistical significant value is given for each paired correlation. So for this output, the correlation coefficient R needs to be less than 0.8 and also need to be greater than minus 0.8. So the R value, the reasonable acceptable correlation coefficient between items, need to be less than 0.8 and greater than minus 0.8. And if the R coefficient is greater than 0.9, then delete one of the items or take the average for both items. If the R value is less than 0.3, then there is a weak correlation between the items, need to be deleted. If the R value is greater than minus 0.3, then delete the items as they show a weak correlation. In this output for correlation matrix, there is also an important value here, which is the determinant. It has to be greater than 0.401, and here from this table it is greater than that value. So these are the essential important observation and interpretation of the correlation matrix or matrix to consider when looking at correlation between items, the correlation coefficient, and the p-value and the determinant. Moving to the next slide. The next slide describes how to check the adequacy of sampling by performing a Kaiser-Meyer-Olkin measures of sample adequacy, as shown here in this small table, KMO and Bartlett test. The test shows that the value that need to be acceptable has to be greater than 0.5, and ideally 0.8 will be the best value. So when performing factor analysis, to accept the method for analysis, certain assumptions have to be fulfilled. This is one of the assumptions to check for the sampling adequacy. The value should be greater than 0.5. And the Bartlett test of sphericity is a test that will test whether the correlation matrix is in an identity matrix. The identity matrix is the matrix with all diagonal elements are 1 and all of the diagonal elements are 0. Then reject the null hypothesis if p-value is less than 0.05. So we need to have the p-value here less than 0.05 and this value to be greater than 0.5. So the output from the factor analysis shows the underlying construct for observed variable or variables, will identify common factors that are common to multiple variables, and also will determine a unique factors. Unique factors are specific factors. Those are individual factor unique to each variable and not shared with other variable. Also, an output from the factor analysis shows the communalities values. So the communalities is the proportion of each variable variance explained by factors. A variable communality ranges from 0 to 1, and extraction values indicate the proportion of each variable or variable's variance explained by factors. So for item number 1 here, the communality is 0.86, the second one 0.5, the third one is 0.4. Anything less than 0.3 has to be removed from the analysis. The output for the FA analysis will also shows the factor loading. A factor loading is a measurement that indicates the strength and the direction of the relationship between variable and a factor. So high factor loading suggests a strong relationship. As shown here in the pattern matrix, there are here 1, 2, 3, 4, 5, 6, 7, 8 items have been grouped into 3 factors, factor 1 and 2 and 3. Factor 1 have 3 items load into it, or these 3 items, item number 1 and 2 and 3, measure for that factors. And as shown here, the loading value is 0.93, 0.7, 0.65 for the 3. So these 3 items hold together to represent or measure a factor. For factor 2, item 4, 6 and 5 hold together and load together to that factor. So it looks like they measure this factor. And finally, the factor 3 consists of item 8 and 7. They are loading into that factor with a value of 0.87 and 0.57. The right hand table is also a factor loading for rotated factor matrix, so which is part of the factor analysis. So one of these tables for principal component analysis, and the other one for exploratory factor analysis. So this output or representation that is generated by the factor analysis shows the loading for each variable or items to the specific factors. For the pattern matrix, you need to have a value or a factor loading value greater than 0.3. Any value less than 0.3, then omit or delete that item from the analysis. Another value that is essential when pre-performing the FA analysis is the eigenvalues. These values represent the variance explained by each factors. The higher the eigenvalue, the more variance is explained by the corresponding factor. So here a table extracted from FA analysis for items in a questionnaire, and as shown here, there are 8 items and only 3 factors, factor 1 and 2 and 3. This table shows the total variance explained by the factors. And if we look at the initial eigenvalues, percentage of variance, we see that factor number 1 explain 27.6 of the variance, factor 2 25.7, factor 3 18.9. These 3 factors, they explain 72.36% of the variance. So these 8 items can be grouped into 3 factors, 1 to 3, and those 3 factors can explain or retain 72.3% of the variance. This is a section extracted from factor analysis in SPSS. This is a factor analysis for principal component. The scree plot is ticked, and the extraction based on eigenvalue set up to be greater than 1. In addition, also to look at the table of the total variance, a scree plot can be generated. A scree plot is used to visualize eigenvalues, identify point at which the curve level off, suggesting the optimal number of factors to retain. So this diagram shows on the x-axis is the factor number, and on the y-axis is the eigenvalue. The eigenvalue is set up at 1, and there are 8 items have been sorted into 3 factors: factor number 1, factor number 2, and factor number 3, and the cutoff point is 1. So there are 3 factors that can be generated when the eigenvalue is set up at greater than 1. There is also an important section when performing factor analysis is to choose the rotation method. As shown here, there are 2 major types of method for factor rotation. The first one is orthogonal rotation. Orthogonal rotation includes varimax, equimax, and quantimax. Those 3 types of rotation are used when there is no correlation between factors. The second type is oblique rotation that include promax and direct oplement. This type of rotation is used when there is a correlation between factors. So the method for rotation to select from are 5 different possible methods: varimax, equimax, quantimax, direct oplement, and promax. This can be done in SPSS. An output from the factor analysis will generate a factor scores. Once these factors are identified, rotated, and the items that load into these factors are identified, then factor loading scores is calculated for each items, and group of items that measure and load into the factor or the construct are also identified. So a group of items will measure the factor or the construct or load into the factor and construct. However, the FA analysis will only generate the number of factors or construct that can be obtained by performing the FA. Then the statistician has to give these factor a proper label or name that represent what these items are measuring. In this presentation, 2 methods, statistical methods, will be compared: the factor analysis and the principal component analysis. Factor analysis and principal component analysis are related. They are similar. However, both are not identical. Both are statistical multivariate analysis methods aim to reduce the dimensionality of the data. That is the common things between these two methods, abbreviated as PCA and FA. PCA is merely mathematical technique or method that aims to reduce the data dimensionality, i.e. reducing the number of items. It is frequently used in survey and questionnaire analysis to reduce the large number of items or questions through the method of principal component analysis. Factor analysis, on the other hand, is designed to identify unobservable factors from observed variable. It aims to identify latent factors that explain the correlations between observed variables. So there is a subtle difference between PCA and FA. PCA is a data reduction techniques, reduce the number of items. FA is designed to look for latent factors. So both have different approaches and assumptions. Choosing which one to use, whether PCA or FA, depend on the underlying assumptions of the data and the objective from the research study. PCA is merely dimensionality reduction technique. It aims to group set of variables or items or questions from a survey or questionnaire into a new set of uncorrelated variables called principal components. That is the main target of or objective of performing PCA, to generate principal component, group these set of or collection of variables into component. These components retain maximum variance in the data. However, the FA is a method to identify latent factors that underlie observed variables in data. Its aim to explain correlations between observed variable via number of underlying and unobserved factors. So there is a major difference between both these techniques. The first one is reduction technique. The second one, search for latent factor. This latent factor will explain correlation between variables when they are arranged into factors or constructs. In terms of assumptions, PCA assumes that principal component generated are linear combination of the original variables, and these components retain or explain the maximum variances in the data. The FA assumes that the observed variables are affected by underlying latent factors. Those observed variables have a unique variance that is not explained by the factors. So FA will look for common factors and unique factors. In terms of the interpretation, the PCA, the principal component or components generated or obtained from the analysis, do not have an interpretation in terms of the original variables. They are mathematical constructs. So these components are mathematical constructs representing variance in the data. For the FA, The factors extracted from the factor analysis are intended to have a meaningful interpretation in terms of the observed variable. Each factor is associated with a subset of observed variable that have high loading on that factor, indicating a strong relationship. So in FA, a construct is generated or factors are produced. Those produced factors have a meaning as they have in them items or variables that measure that construct or factor. In terms of variance explanation, the PCA aims to explain maximum variance in a data by producing a principal component. The first principal component explains the most variance. The second one explains the second most, and so on. In FA, the focus of the factor analysis is not on explaining the variance, but rather than that is to identify the underlying factors that can explain the correlation between the variables within that factor. For rotations, PCA, the principal components produced are orthogonal to each other, meaning they are not correlated. In FA, factor loading are not necessarily orthogonal, and different methods of rotation such as Varimax, Promax can be applied to make the factors more interpretable. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, RStatistic or Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, RStatistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.